All right, well, here's what we're going to talk about today. We're going to talk about methods for how you use the OPD Scan and Station. Boo. All right. So, my ears are too big. All right, so let's look at something. We got a pointer up here. So, a lot of people have been working on this over the last 2 or 3 years. I want to show you the team that we have. Mr. Ozawa, as you know, is retired as the CEO, and now Matoki, his son, is the CEO. And this is the team that we've been working with over the last 2 years. And now Matoki is, as I said, taking over CEO. But a lot of people have gone into what we're going to be talking about today in terms of the power of the cornea and how we use the OPD Scan and Station in a way that gives us the best results. Now, when you look at this, here's the thing. The OPD scan is what we would call today a wavefront analyzer, but the wavefront measurements that are taken are not like a Hartmann-Shack or like a churning aberrometer. It's an aberrometer that we'll see uses the same principle that's used for retinoscopy, and that is it looks at the scan of a slit being moved across the eye. Now what that does is it means it doesn't have to do any Zernike transforms, it doesn't need to do anything. What it actually does is it maps the refraction at every point in the pupil and then makes a map from that and then goes from there. So the first thing that you get is a refraction that is extremely accurate. Thank you so much. Now let's take a look at that. So when we look at this, what we'll see is OPD scan has a keratometer and an autorefractor. It's got a topographer, a pupilometer. It also tells us about the aberrometry in the eye, tells us about the wavefront, calculates Zernicke's, point spreads. All these things are important to us in evaluating the quality of a person's vision, and we're going to talk about each of those. Now, that's what the unit looks like: autorefractor, keratometer, topographer, pupilometer, and aberrometer. And what happens is this. Let's talk about these individually. Now, we got to talk about a few things. One of the things that I've told the people at Nidek and other companies is doctors don't have time to sit at a unit and pull up images and look at different things. It's nice, but you don't have time to do that. What you want to be able to do is you want to have a map, a report that's in the chart, so when you sit down with the patient, you can look at that report and tell you everything you need to know about the patient. Well, the first thing that we've had for many, many years is an axial power map. This axial map that we have right here. Now, that axial map is the map that you've looked at for 25 years. An axial power map is the map that allows you to see things the way you've always seen them in terms of bow ties and other things, but it's an axial power map. So there's not much time we need to spend on that except to say one thing. An axial power map is always relative to this axis, and so all measurements, as that goes up, that radius is always referenced back to the center of the Earth. So if we looked at the radius on the center of the Earth, we'd say it's 4,000 miles to the center, so we'd have a 4,000 mile radius if we walked along the surface of the Earth, right? And when we got to Mount Everest, it's 6 miles high, so we'd say we're at 4,006 miles, so it doesn't show up as very much difference when you go from 4,000 to 4,006. But that's what an axial power map is. Now, an instantaneous radius of curvature map, or a local radius of curvature, or what we've referred to in the past as a tangential map, is not relative to the center of the Earth. On this map, when we walk around here, that curvature is here. This little bump right here has a radius right here. So if I'm standing on the top of the Earth and I'm 4,000 miles from the center, and I put a little 10-foot dome right here, and I stand on top of that hemisphere, I'm now 4,000 miles and 10 feet, but the radius of that dome is 10 feet. It goes from 4,000 miles to 10 feet. Shows up as a big red mark. So the tangential or local radius map is much more sensitive in showing the geometry and the axial map is better for optically showing, because the power of a surface is related to the center of the earth, but the geometry of that surface is better detailed when we look at the tangential map. So the tangential map shows us little bitty details. So that same picture here we see, like on the previous one, bow tie. When we look at this one, all the little detail of the shapes show up on the surface, so the tangential map is much better at looking at the detail of the geometric surface. So, local radius map is detail, axial power map is big picture stuff and powers. Now, when we look at this, what we'll see is the other map that we have is a refractive power map. On a refractive power map, what we're interested in is knowing is the change in the refractive power over that surface. So it's not the same as an axial map. If I have a sphere, all right, and a sphere is 7.5 millimeters in radius, if I show a map of a axial power map, it's 7.5 millimeter radius everywhere, so the map looks green. But if I have a surface that is spherical and I send a ray in the periphery, what happens in the periphery when I bend a ray at a peripheral surface? It bends too much. It's called spherical aberration. And the reason it's called spherical aberration, because a sphere has rays that come in that bend too strongly in the periphery, and Snell's law explains that. So a refractive power map gives you the refractive power as you move across the surface. So if we looked at a surface that was a sphere, unlike the axial map that would be green everywhere, on the refractive power map, the power would increase as we move to the periphery due to the spherical aberration. So a refractive power map shows you the surface power, an axial map shows you relative to the center of the earth, and a tangential map shows you the geometry. So, the nice thing about that then, we can look at the Placido-Dismeyers, we can have our axial map, our instantaneous map, and our power map. All of those things show us something different about the eye. For example, right here we see the little detail that if we were going to do some kind of laser treatment, we'd want to know that that bow tie wasn't exactly symmetrical and it's got these little changes up here. If we want to treat that from the standpoint of affecting the patient has a pupil that's moved from here and moved up a little bit, well, we'd know exactly how much power change there would be from somebody that had an updrawn pupil from cataract surgery that moved up. We know what their refractive shift could be from here to right there. If your pupil were right here, you wouldn't have any astigmatism, but you'd be stronger in power. You can't pick that up here. So the refractive map shows you power changes, shape changes, and the axial map. All right, so the point is all of those are in the software on the OPD scan and lets you get a good idea of what's happening to the surface. Now, the other thing that it does is aberrometry. Now this is, we want to spend a minute on this because this is important. There's different kinds of aberrometers on the market. There's Hartmann-Shack, which is what the wave scan is, that is made by AAO. There's churning. Those take a matrix, send light in, brings back out, and by how the spacing of that matrix is, they figure out what the quality of the optics of the eye are. That's not the way it works when we use what's called a time-based system. It's the same thing you would do when you do retinoscopy. In other words, when we do retinoscopy, what you do is you look for a slit and you look in the eye, and what happens? If you move the slit this way and the retinal image or the pupillary image goes this way, you know there's too much power in the system. So you add minus when you're refracting a patient, right? If you do that patient and they move together, you know that the patient doesn't have enough power, so you start adding plus. And when you get to the point where it's not going like this, and it's not going the same way like this, and it gets to where when you do this it doesn't move and the whole eye is filled, you know you're at neutral, and that's the refractive error of the patient. Well, that's exactly what the OPD scan does. It's just a high-powered retinoscope, because look what happens. Sends a ray of light in, hits the retina. That retina then comes back out. We got the same scan that you're looking at on retinoscopy. The difference is now, instead of us looking at that with your eye, it's got a series of LEDs in there that pick up the light.